This video goes over sample space diagrams, which is just another way to organize the outcomes of an experiment, different than a Venn diagram. So a sample space diagram, which is also called a probability space diagram, is just another way of showing all the possible outcomes of an event. You can list all the probabilities as long as there aren't too many. For example, this is a sample space diagram of the outcomes of rolling 2 die. So you could roll 1, 1. You could roll 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Same thing if you roll a 2, and you can fill in all of probabilities or possibilities here. 2, 6. You should start to see some patterns emerging as you fill in all the possibilities in this sample space diagram. 4, 4. But as you can see, this does have its limitations. Obviously, if you had too many possibilities or too many outcomes, this method is challenging and a little bit time consuming to write down all the probabilities. Okay. If 2 dice are rolled, find the probability of rolling doubles. So let's circle those here. So where are my doubles? So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So my probability of rolling doubles would be 6 over 36, or 1/6. Now, what about rolling a sum of 4? So I'm going to circle those in green. Let's see. 1 and 3 add to 4. 2 and 2 add to 4. 3 and 1 add to 4. And so I've got 3 out of 36, or 1/12. That's my probability of rolling a sum of 4. My last one is rolling a sum greater than 10. So let's do those in red. So where am I greater than 10? So 5 and here's sort of the diagonal row that's going to equal 10. So the only way for me to score more than 10 would be 1, 2, 3. So to roll a sum greater than 10, I would have 3 out of 36, or 1/12 again. So it's nice because you can count your outcomes and then determine your probabilities from there. Let's look at another example. In an experiment, a coin is tossed and a dice is rolled. Draw the sample space diagram for this experiment. So that's going to be our chart below. Find the probability that in a single experiment you obtain a tail and a number greater than or equal to 3. So let's fill in 1 head, 1 tail, 2 head, 2 tail, 3 head, 3 tail, 4 head, 4 tail, 5 head, 5 tail, 6 head, 6 tail. So what we want is the probability that we're going to roll a tail and we're going to get a value that's greater than or equal to 3. So on the bottom, I'm going to put my total number of outcomes, so that's 12. And now I'm looking for all the ones where I get a tail and it's greater than 3. So my tails already restrict me to the bottom row. And then I've got 1, 2, 3, 4 possibilities where I'm going to roll a tail or greater than 3. And that's going to simplify to my probability of 1/3. This is going to lead us into the product rule for independent events, which is another item to consider when you are solving equations. When a dice is rolled and a coin is tossed, the events are considered to be independent because they don't influence each other, which is an important criteria when you're thinking about events. So we have let's let H represent the event that the coin is heads here. So we have our probability is going to be 6 over 12, which is 1 over 2, okay, in our dice and coin experiment here. Then if we let L represent that the dice is less than 3, we've got our probability here. Less than 3 would be 4 possibilities, so 1/3. So now we want to figure out what's the probability of heads and greater than 2. We can actually just multiply those two. What do I have? Oh, greater than 2. Did I get the right number here? Represent that the dice is going to be greater than 2. 1, 2, 3, 4, 5, 6, 7. Whoops. So we should have 8 here. So we've got probability that the dice is going to be greater than 2 happens 8 times, which would be 3/4. So we can actually just multiply those two together, making sure you're using the right values. So we've got 1/2 times 3/4, which would be 3/8. So I'll write the note on the next page. So we can note that 2 events are independent if the occurrence of one does not, I'll stop writing because it's down there. They're independent if the occurrence of one does not affect the chance that the other occurs. If they are independent, then this is true. That is all about sample space diagrams and connecting to independent events. This example goes over how to apply the product rule for independent events as shown here. So we have 2 bags. One bag contains 3 red and 2 white balls. Another bag has 1 red and 4 white balls. So the first question that we're going to look at is finding the probability that both balls are white. So the probability that we get a white ball from bag 1 is going to be 2 out of 5 because we have 2 white balls and 5 total balls. The probability that we get a white ball from bag 2 is 4 out of 5. The probability that we're going to get a white on both draws is 2/5 times 4/5, which would give us 8/25. The next one is figuring out what's the chance that the balls are going to be different colors. We have 2 situations where they're going to be different colors. So the first situation is if we get a white from bag 1, and then we get a red from bag 2. The second situation is a probability for red in bag 1, and then white in bag 2. So to get white in bag 1, our chance would be 2 over 5. Then to get a red in bag 2 would be 1 over 5. So this would make our chance as 2 over 25. Here we would have red in bag 1, white in bag 2. So red in bag 1 would be 3 out of 5 times 4 out of 5 to get a white in bag 2, which is going to bring us to 12 out of 25. So therefore, our probability that we get different colored balls is the probability that we get white first, red second, plus the probability that we get red first and white second. So we're going to have 2 over 25 plus 12 over 25, which is going to equal 14 over 25. Okay. The last one we're going to take a look at is to see if one ball is red. So the first one that we have, the option that we could do, is we could find the probability that we get a red twice. That would be at least 1 red. Add the probability that we could get red first and white second, and then add the probability that we get white first and red second. Not too hard. We'd only have to calculate this because we have this and we have this from option B, or from part B. The second approach that we can actually do is if we have at least one red, we can do that as 1 minus the probability that they are all white. So we've got 1 takeaway 8 over 25, which would be 25 over 25 minus 8 over 25, which is then going to give us, let's see, 25 minus 20 would be 5, which I think would be 17 over 25. That would be our probability for at least one red. You can write it in words or you can write it in mathematical